Okay, so your written test number 2 tomorrow during the lab session 9 a.m., right, for 15 minutes, just like a written test number 1. So today I'll try to leave maybe about 20 minutes at the end so guys can ask me questions, and then I can give you guys more explicit tips about what you can focus on for study. Since I am not able to provide some example question this time, but I can give you some tips about the test tomorrow. I'll leave 20 minutes for that, okay, at the end. But let's cover some material first to make sure we are still smooth in your learning, okay. Your lab number 4, that'll be the last lab. I'm going to release it tomorrow after your test. So you will have until, I'll try to push that to the very last day that you can turn in the term work. I'll try to push that, okay? And for office hour, you can definitely see me today at 3 p.m. or even tomorrow if you want to talk about maybe your progress in the course or any other materials for this week, you can still do that. And again, if you want to reach out to Andy about the labs, you can also feel free to do that, okay? Any question about the course? All right, sounds good. Excuse me. All right, let's now talk about some recap from last time. So we've tried to finish the very few last bits about the LTL, namely the binary operators, basically. So what we're considering is, just before that, let's see here. Yeah, exactly. So before Monday, so we were talking about the different unary operators, you know, the X operator, the global operator, and the future operator. And what we did on Monday was we introduced some binary operators. If you check the grammar for the LTL, you'll see all these are the operators that we listed in the possible grammar. So the first one we did was the until operator, and then we did the weak until operator, and also we did the release operator. Okay, so you guys should really dive into the formulation for each of the 3 operators and see how they're supposed to mean, and then how the universal and existential quantification are being used. Of course, the more complicated one is the until and also release operator. I just want to mention very briefly. Of course, for the precise detail, you got to watch the recording and then review the slides. Let's say, for example, let's say if you got a weak until operator right here, okay? That one there is going to reuse the until operator right here. That's one of the possibility. So that's why it's called weaker. So the weak until is going to accommodate not just the scenario where the until is going to satisfy, but also it's going to accommodate another one. So that's why we have this junction over here. And just notice that the fact that we're referring to the until here, that means the universal quantification is also within over here. Right? So that's the thing you want to watch out for. Okay. And you can, let's now just do this visual summary quickly, right? So we're going to do some exercise today just to do the final bits about these 3 operators. So we got, let's say, phi 1 until phi 2, right? We say that there exists some future point, phi 2. And all we require is for all the states starting from the first until I minus 1, they should satisfy phi 1. We don't insist that phi 1 should also be satisfied in phi 2. We don't insist that. It could or it could not be, right? So that's something you want to watch out for. And we'll see some example today, like how we can check for model satisfaction. And the weak until over here, basically the first scenario is just the same as the until. And then we allow another scenario to make the weak until true, which would be if the first formula here is simply globally true, always. That's okay. Okay? So that's really the difference between the 2. And then the release operator here, so we got phi 1 releases phi 2. They're kind of similar to the weak until, so that's why you got to do some comparison, okay, by comparing their formulation. Scenario number 1, you're saying that phi 1 at some point must be true, at which point you're going to release the truthfulness of phi 2. And you kind of insist that when phi 1 is actually true at this point, phi 2 must be true at this point as well. So notice that this is really important here, the condition. So there must be a future point where phi 1 and phi 2 are both true. And before that future point, phi 2 must be true, right? So that's the formulation you want to watch out for. John, give me one moment. Okay. So that's one thing you want to watch out for. And then the second scenario is very similar as before. So phi 2 may just be true always, in which case you can also satisfy the release operator. So we're going to see maybe a little bit, I kind of missed one, like a formulation for English in the LTL example. We can do it again. And that one is going to use a release operator, which I'm going to ask you some question for which you got to check the formulation to really get the answer. Okay, we'll get that a little bit later. John?
Yeah, so for all 3 of these, they have to start from the beginning of the path, right? So maybe this is better in a concrete example, but like if you say like pi 2 satisfies this, it will be the path starting at pi 2 and all the way to it, right?
Okay, I see what you mean. So here, of course, all the definition about path satisfaction still actually apply. For example, let's say this. Okay, let me just start a new page over here so we can benefit from that. So, for example, if you say, let's make it a little bit more abstract, but go right to your point. Okay, so if I say, for example, pi satisfies, let's say phi 1 until phi 2. Okay, versus if I say pi 2 satisfies phi 1 until phi 2. Let's say what the difference is between these two. Okay, let's say we're considering the same pi. Okay, so let's say this is pi, infinite path, and this will be state number 1, state number 2, state number 3, etc. Right, and the same path as well. Okay, let me just copy that, and then we got over here. Okay, right. So when you check this satisfaction for the path, right? So what you're doing is you're saying, starting from state number 1, we will check this formula here according to its formal definition. Okay, and now if we say pi 2, right? First of all, let's figure out this pi. It's going to give you basically like a new path, and the new path is going to be like this, starting from here. This is pi 2. This one here is actually pi 2. So everything that's going to be according to the formulation is going to consider everything starting from state number 2. Okay.
So state number 2, phi 1 has to hold up until phi 2.
Something like that. So we are saying that, for example, starting from state number 2, there's got to be a future point that will satisfy phi 2. And then that state, like I minus 1, right? Okay, let me make it more explicit. You can think about as far as pi 2 is concerned, this one here is like a state number 1. This is like a state number 2. And all the way to maybe some I minus 1 and also some I over here, right? So we'll say that for I is going to satisfy phi 2 at some future point. And then all the previous point will exist basically from here. Okay, maybe it's better to from here all the way to I minus 1 relative to pi 2. They should really satisfy phi 1. Right? So the definition will still go relative to the pi you are talking about. Make sense?
You could say something like there exists some state where this holds, like anywhere.
Yeah, you're gonna say there exists some states that phi 2 is gonna be satisfied eventually. But here we don't really consider state 1 anymore. Okay? That could be where the confusion was. So we're saying that this one here is not relevant. Not relevant anymore for pi 2, right? Okay, it's a good question. Okay, all right, let me go back. All right, so we talk about all these three, right? You can review them. I think that this visual summary here is very important, right? You really got to see the release over here. So insist these two must be true at the same time for one of the scenarios. Yeah.
So when we say that both should be true at the same time, where does that come from within the definition, like within the mathematical definition?
If you look at that definition, you will see less than or equal to. You'll see that equal sign over there.
But isn't that the same for until as well?
But you got to look at exactly a bound value. One is about I minus 1, the other one is I. So pay closer attention to the formal definition. I know exactly what you're asking, so I'll encourage you to go back to the formulation. You will see that for until over here, it will be less than or equal to I minus 1. But for release, it's going to be less than or equal to I. The subtlety here is very important. All right? Okay. All right, anything else? Okay, awesome. And that's about a recap. And the formulation, you guys can review the example. One thing I want to correct, I think your fellow student asked last time. He was absolutely right. So the correct answer, which I didn't pay close attention to, you can simply say something like, so this one here, let me cross it out, okay? What should be the fix? You know what, let me just do this. So you will also get these updates from today's notes. The correct answer is on the slides anyway, but I just want to also emphasize again. So When you study the slide, there should be no confusion. Okay. So about this smoking example here, we already introduced it. We spent quite a bit of time. You can refer to the lecture recording from Monday. But here the correct answer should be, so for this part, okay, it would be sufficient to do the following. I think what I said last time was a little bit too unnecessarily complicated. All we got to say is, I smoke until, so here we're going to say that I don't really smoke anymore after I was 22. That's really what the English sentence is meant to say. So what I would say is, I'm going to say, first of all, I was 22. First of all, you got to be satisfied first until this is satisfied. And also, from that point onwards, I don't smoke. Right? You can see that's the negation of that. Right? So when you study for this example here, I want to point out one more thing for you to really notice. Okay? You want to say this G operator is relative to the future point where I was 22. Starting from that point, I was 22. From that point onwards, I don't smoke anymore. So this global property starts to hold at the future point where I was 22 is true. Okay? That's really the new bits I'm adding here. Okay? This global point is really relative to when I was 22. All right? And you can definitely try to look at the formulation here, try to see if you can plug in these formula over here. That'll be some good exercise for you. That'll be kind of nested quantification. You can try. Okay? All right, so that's about this example here. And then we spoke about others last time. Let me just go very quickly. And then we talked, this one here, it's just using a future operator. And we kind of illustrated to you, these are the nice property you can have, right? You can easily prove it by just unfolding their formal definition using predicate logic. And then we got this one here. It's a very nice pattern, all right? So it is always the case that if you make the request, then at that point, there will be a future point that you got acknowledged. I think Daniel can ask me for some clarification on Monday. I also explained that about how to understand it. You can also refer to the lecture on Monday. So you can also see some clarification. Okay? And that's the elevator example. And then you should really know why just having global here is actually not right. Right? You want to make sure you understand using different operator, what can be the consequence, right? Sometimes it may not just be faithfully representing the meaning from the English. I want to do one more. Okay, this one here, which I kind of missed from last time. Okay, read it please, first of all, and then we'll see how to formulate it. The key terms I can highlight for you. Something like that. So what you really want to think about is, how do you formulate, for example, whenever? That one sounds like a global property, actually, whenever, right? It must be continuously the case. And as soon as, do you think this sounds more like a global or future operator? As soon as. That means whenever, as soon as means when it happens, right? Does it really happen all the time? We don't know, right? As soon as. Think about that kind of differences, right? I might kind of change the language for the test or exam, so just gonna kind of work out the exact formulation. Anybody want to try before I actually give you the answer? I don't mind giving you that directly, but if you want to try, might be a nice time for you to give feedback. How do you formulate this? And all the assumed atoms over there is something you have to use. Anybody want to try? Daniel, go ahead. Global operator, I agree. Why don't I do that first? What do I put? It is always the case. And then?
Making one part just be if it makes a request.
If you make a request, right? So that means I can say requested. As if requested is true, if there's no request, I don't care. In that case, should I use some logical operator over here? Implies, yeah, that's good. Very promising. How about after that? The consequence over here might require some sophistication. Because we say that you kind of stop waiting. Pretty much like I say start waiting until the point that somebody or nobody is in the critical section, so I can enter, right? That's kind of the internal dialogue you want to have with yourself. Okay, I'll put it down for you. But I think if you can already reach this pattern here, that's pretty good. Okay, so I can say no one in the critical section. No one in the critical section. As soon as this one happens, it's going to somehow release the condition for me to wait. So I can stop waiting, basically. Okay, this one you can definitely try to put a little bit more thoughts into it. So release.
So that means there's one state where no one in C and waiting are both true?
That's a very good insight. Let me write it down first. Okay, and let's see why it is important, right? So you can see if we use a release operator, this one tells us that no one in CS and also waiting should be true at some future states. Yes, indeed. As soon as we get to that future states, that means it's the time to grant the access to the critical section at that point. So that's important. Yes.
Could you repeat that once again?
Of course. So if you look up the definition for the release, okay, let me show you the visual summary again. So the essence about release is there should be a future point. Let me show you exactly where it is, right here. There should be a future point where both formula must hold true. In this case, let's say here, this will be when nobody is in the critical section. And then I have been waiting until this point. I'm still waiting. If these two conditions are true, that will be the point I can grant the access. Okay, good. And it turns out for this condition here, we shouldn't even need to worry about granted. I don't think it's really necessary. I can get rid of it. Okay, we don't need it. Okay, good. And some question for you to think about. Like what you guys learned back in the operating system course, what does a starvation really mean for the process? Anybody can recall? What's really starvation?
One process pointing to the other is pointing to the other, but like there's...
That sounds more like a deadlock or lifelock situation, not exactly starvation. Mm-hmm.
It's just a process waiting for it to be granted the approval to enter the critical section that it gets.
Exactly. So you starve, right? Yeah, exactly. Well, a typical problem is a dining philosopher. I'm pretty sure you guys heard about it, in the operating system course, right? So it is possible maybe the philosopher, they simply don't get anything to eat for the spaghetti, right? So they just starve to death. That's a methodology, that metaphor. Okay, starvation freedom is really guaranteed. So, which is asking, is it possible for a process keep waiting and never granted access? Is it possible? According to the definition for release. Okay, that's something you guys want to think about as exercise. Okay, i.e., is it possible for a process to keep waiting without ever being granted access? Ever being granted access. All right, think about this question here. But once you actually look at the formal definition for release, it should be quite clear to you. All right.
So why are we not using until? Because in the description it says it starts waiting as soon as
I think the reason we are not really using until is, as you actually asked the question, right, about release, we really want to get to the point where both of these are true. So we know that it's safe to really, at that point, to really give them the access. We want to make sure when nobody is in the CS, but you're still waiting. Both must be true at that point. But if you use the until, it's not going to insist this point. That's the reason.
But there could be a case where no one in C is true and is waiting is false.
Until may actually have that, but it doesn't insist that. But the release will insist that. So release is a more accurate operator to ensure that.
I guess I'm confused about the description because it says as soon as, right? So
Yeah, as soon as, right? That means at that point, you should really make sure the process is still waiting, and also the nobody else is in the critical section. It basically is more like a judgment. So is it really important when nobody else is in the critical section, but if the process is now really waiting, what's the point of granting the access, right? You really want to think about what was the difference between these two. Why not use until, right? Because when no one in CS is true, waiting does not need to be true. It's just I minus 1, right? Not exactly I. That's really the insight into why you would choose one but not the other. Yeah. All right, it's a.
So when no one in C is true, then the other process shouldn't be even waiting. That's what I'm trying to say.
No. So what we're saying is when nobody's waiting, if you want to grant this particular process to really to enter the critical section, they must be currently waiting. Maybe for whatever reason they are not waiting anymore, then what's the point of granting them the access? That's really the point, right? Let me visualize the bit, okay? So let's say for this one here, let's say that's the timeline, right? So there is a point where no one in critical section, all right? Until will be okay if I say at the previous point, I'm still waiting. That's until. But it wouldn't insist that at this point here, waiting should be true as well. It wouldn't insist. So that's why it's not accurate enough, not strong enough. But at this point, we want to make sure before you grant the access for this particular process, nobody should be in the CS, and also that process must be still waiting. So it will make sense to give them the access. That's really the point, okay? Okay, so both of these must be true. So that's the meaningful release, okay? So I think this example here is also a very nice way to illustrate. Sometimes you may want to release as opposed to until, or weak until, right? All right, that's good. We have done about 4 or 5 examples about formulating English into LTL. You guys can definitely learn from these patterns over here, and then shouldn't be too difficult if I give you something similar, maybe in the exam. And also, I might, as I said on Monday, I might give you the English description, and I'll give you some candidates description. You can choose the one that's most accurately explaining the pattern, or maybe justify why it is not appropriate, right? Things like that. Okay. Any follow-up to this, Daniel?
Why didn't we use granted? Why didn't we use granted?
Yeah, actually, this example here, I'm just meant to just say that condition there. We can add granted, maybe in some other context. I'll say let's not overcomplicate over here. That'll be enough. Yeah.
So Professor, let's say in exam, if you give us assumed patterns, there would be a case where if we don't use 1 or 2 of the given patterns.
Yeah, I think since this more, I see exactly what you mean. So I'll be very clear. I might say out of these atoms, you might use, maybe you must use all of them. I'll be very explicit. Well, I might say you don't really need to use all of them. Choose the one that are relevant. Yeah. Yeah.
One granted atom, could you like nest everything within the global, like as another implication?
Yeah, adding the granted may not be so straightforward. So I'll say I can discuss that maybe in another later session. I can talk about it. But for now, let's not worry about granted. It's more about a condition to say there's got to be such point where you can actually try to grant. Yeah. Okay, good. All right, let's now do 2 examples on the model satisfaction for weak until, and release. Okay, so 2 more examples, and then we can conclude the LTL lecture. And Oh, by the way, so if you look at the lecture site, just in case you haven't seen that, I didn't really announce that explicitly, but it's already there since yesterday. So if you go to the lecture site, let me show to you. Give me one moment. So 4315 over here. It's right underneath the slides. So you will see that under here, exercises, solution. So if you click on that, that's basically all the exercises I kind of suggest that you guys can do. Right? You can check, if you have done the exercise, you can double check the answer. For many of them, they're quite straightforward, but I also try to put some justification whenever needed. So I think that this will be very useful for tomorrow. I'll talk a little bit more about some tips for tomorrow for the written test. And the two exercises we're talking about today, about until, week until, and release, I'll post a solution as well, maybe a little bit later. Okay. John.
Just a question for the starvation freedom. Can we go back to that slide?
Mm-hmm. Yeah, now you know how to find the exercise solution. There we go.
So this starvation freedom is saying that there's a case where that your question is true.
What you got to think about is, okay, good. So I wouldn't want to reveal the answer just yet because we want to think about it, right? Okay, let me make the question even clearer to you. Let's say if you got this particular pattern over here using the release, would this formulation here allow a possibility where a process, once it's been waiting, you will never get granted the access, ever? That's something you want to think about. And to really answer that question, all you got to do is look at what can make the release true. If one of the scenarios to make release true can result in starvation, then that means this is not starvation free. Okay, that's something you want to think about. Okay. All right, let's now do some exercises quickly. Okay. The first one here. Okay. So now we're talking about S0, S0, S0. And after today's discussion, you can think about S2. All right, that's something you can do. All right, guys, the first one, S0, P until R. All right. If you think that's true, you got to consider all the possible paths. If you don't think that it's true, you have to give some witness. Any suggestion? Of course, if you haven't been familiar with the formulation here, it might be a little bit challenging, but just in wondering. Adrian, go ahead.
I believe that P until R is true because no matter what path you take, the first state will be S0, which has P, and the second state will be either S1 or S2, which has R.
Yeah, quite a nice way to say, yeah.
R.
Exactly, quite a nice way to say I minus 1 and I, right? Quite a nice one. Yes, I agree. All right, so this one here will be true, but let's now try to make it a little bit more explicit for you. Okay, so this one here will be true. And to really think about S0, which will be here, the reachable states from S0 will be either S1 or S2, right? Either way. So you can think about, you can go from S0 and then to S1 and so on. You can also go from S0 and then to S2 and so on, right? So these are the two possible patterns, okay? And you can nicely see that for P, it's, let me say in the other order. Let's say for the R over here, it's actually satisfied in S1 and S2. Right? If you see S1 and S2, you definitely got R. Right? So this is like the future point where R is satisfied, like a phi 2. Okay? So for both of these, R is satisfied. And until tells us you don't really need to have P true at the same time. That's for release. But now you only insist in the previous states. Think about this is I, so this will be I minus 1. So the P must be true for all the states starting from 1 until I minus 1. But in this case, there's only one state before that. Okay? So now S0 over here is right here. Does it satisfy P? Indeed. So P until R is good. Okay? So S0 over here satisfies P. So if you like, you can think about this is like I minus 1. This is like I. Okay? All right, any question about this one here? Okay, it's a very, I'll say a very straightforward scenario to see how the until is satisfied. Okay. How about this one here, weak until?
It's going to be true. One way could be that because P until R is true, that's why it's true. But the other way is that we can also provide paths.
Exactly right. All right. So this is something we also discussed last time. So weak until is actually a weaker property. So if you think about the diagram again, if I got, let's say, P until R right here, then P weak until R would be something strictly more tolerant. Weak until R. And I know that this guy here already satisfies this one here. Then, of course, it must satisfy this one as well, diagrammatically, for sure. Right? So if I give you this question directly without having to solve this one here, so there are two ways for you to do it. Either you try to say P until R is true. That would be one way to prove it. Or you can try to say maybe P is always true. That's the second condition for weak until. Okay. Because P until R is true. The stronger one already satisfied. Of course, the weaker one is satisfied automatically. Okay, that's the point. Alrighty, how about this one here? Release. Again, similar. If you believe that's true, give me some justification for all the path pattern. If it is false, give me a witness path. Okay, John, go ahead. I'll let you try this time.
S0, S2, P and R aren't satisfied at the same time.
Okay, that's one thing. True. Okay. For this one here, let's be a little bit more cautious here. Okay, let's now do this more properly. Why don't we recall our definition for release? Let's be more careful here. We have to skip space to do that. And specifically, I'm going to think about this. I'm going to replace the formula as well. You guys can also check the formal definition. If I say pi, certain path, satisfies, in this case, let's say R releases P. Right? Exactly what we got here. R releases P. And you can plug in the formal definition, and this is what you will get, right? I'll just write it down directly. We basically got two criteria. If either one is true, the release will be true. The second one is actually very easy to see. Just globally, P. Right? If it's always true, there's no point to release it. No way to release it. Okay? And then the first one here is going to be there exists I larger than or equal to 1, and over here, pi I satisfies R. And for every j less than or equal to I, right, it's a release, so there's no I minus 1 here. And then implies pi j satisfies P. Okay. So this one turns out to be false. This formula here, I can tell you. This one here turns out to be false. Because we can find a witness path where there is no such future point, where R is actually true. That P is, beg your pardon. Let me say that again. I look at the wrong thing, okay? So we want to disprove this one here and also disprove one here. Okay, I'll write it down here. Sorry for the confusion. So we got 1 and 2, first of all. 1 here and 2 over here. To really show that release is actually false, we're going to show that 1 is not the case and 2 is not the case. Okay? The witness path you can consider will be here. So witness will be S0, and then S1, and then S0, S1, etc. let's say this is a path we want to consider. S0, S1, S0, S1, let's say this particular cycle here, indefinite. Okay? Why is that one going to make release false? So that's a question, right? In order to show that this path over here makes the release false, we are showing that this part here cannot be satisfied. And also this part over here cannot be satisfied, right? Why don't we start with this one? In this particular path over here, is GP the case? No, because in this one here, you can see P is only satisfied in one of the states, S0. But whenever you reach the S1, P is not satisfied. So GP is not good. So we just show that number 2 is not possible, right? So I'm going to say condition number 2. Condition number 2 is not satisfied because S1 does not satisfy P. So this is going to make this condition here false. Right? That's one thing. And we need another one. Another one here is saying at some future point, R must be true. And at that point where R is true, P must be true as well. Do we have that future point as far as this path is concerned? Well, this cannot be the future point because P is true, but R is not true. And also S1 here, R is true, but P is not true. There's no such point. So that means 1 here is also false. We try both possible ways to really show that release is true, but both fail. So there's no way release is true. All right. This one's slightly more complicated, but I think it's worth doing together, right? You just want to refer back to the formulation. So from condition number 1 is also not satisfied because there is no such future point where R and P is satisfied, right? So R and P is required, but it's not. There's no such future point. Right, let me recap about this last one here. In order to show that the release over here is actually false, you got to show a witness path. And in that particular witness path, you have to say, since in order for the release to be true, you only need to satisfy a disjunction. And we're going to show that this is not possible, and this is also not possible. So there's no way the release can be true for that particular path. Right? Right? Any question about this? Yeah, take some time to digest one. I think this one is slightly more complicated. All right, so you can also do the S2, right? Change the S0 to S2, and then also post a solution a little bit later. I think that'll be also beneficial for your exam later. Okay, let's do one more. And then we'll take a short break. Okay, one more. All right, let's now try to do this one here. Start with this one here. Is it true or false? Until. Ferrets, go ahead. Until. False. How come?
P and R itself is never satisfied.
Yeah, there's no such future point, which is required, right? Good. So this one here is simply false. And I can just give a witness path. For example, I can say S0, S2, and then S2, etc. Where P and R is never satisfied. In order for the until to be satisfied, there's got to be a future point. Right? There's no option there to say this one continuously to be true. That's not a normal until. That's a stricter version. Okay? Is never satisfied. Very good. How about this one here? You can see the phi 1 and phi 2 are exactly the same. I'm just changing from until into weak until, right? Obviously, the until path is not going to work, but weak until has a disjunction. What about second condition to make a weak until true? Can that be satisfied though? Adrian?
The left side is always true, every state as either P or R.
Uh-huh.
So that means the weak until will always be satisfied.
Yeah, the second condition there, right? Okay, good. Let me say that. Number one, we know that P or R until P and R is not satisfied. But globally true, P or R is actually the case for the entire thing. You can see all the states over here, either P is true or R is true. So that's all good, right? It's going to satisfy the second condition. So based on these two, we know that P or R, weak until P and R is satisfied. It's really this second condition here that makes the critical decision, all right? So for release and also for the weak until, it has a disjunction. So really to show it is true, you can just choose one of the disjunct. But to show that it's false, you got to show that both disjunct are not possible, which we did in the earlier page. Okay. How about this one here? Anyone? John, go ahead. Yeah, exactly, right? So that's pretty much, well, we kind of show that, right? Over here, exactly, okay? So one of the branches, one of the conditions is actually true. So for this one here, this one here is always true. That will satisfy the second condition for release, okay? So that's why overall, this is actually true. Overall, this is true. Okay, let me highlight it. That's the overall result, and this one is false. And this one here is actually true also. All right. Right, so these two pages, basically we just do some standard exercises on the operator. But I think now for the temporal operator, we pretty much, that's the last example I want to talk about. You want to be able to do path versus model satisfaction. And also, given some English sentences, you want to be able to formulate them into LTL. Right? So these are the two main things you want to feel comfortable with when writing the exam. All right, any questions? Okay, as far as LTL model checking is concerned, we are pretty much done. I don't think we really need to dive into CTL. That's okay. I think we got today and also 2 more classes next week. We just do some program verification. I think that'll be enough for the semester. Okay. Why don't we, right, so before the break, we finish off the last bit about LTL. Please review them. So for the until operator, weak until, and release, that'll be covering the exam, but not tomorrow. Okay, I will leave. I think I can cover program verification just for about 10 minutes. I'll leave 20 minutes if you got any questions, okay, just in case. All right, just 10 minutes. We'll cover some very basics, and they'll do the more deeper discussion maybe next week for 2 lectures. That should be enough. All right, so program verification, I'm going to get rid of this. You don't need to read anything, okay? I think slides should be enough. All right, we're going to learn about program correctness and then learn about Hoare triple. All right, it's a very important idea about program verification. I'll give you the context more, the detail about Hoare triple on Monday next week. Weakest precondition. Okay, we'll talk about precondition in your lab number 2. What does it really mean for the precondition to be the weakest? Why are we talking about the weakest precondition? And then there will be some rules you have to learn about WP calculus, but for those rules, you can feel free to put them on the data sheets for the exam. That's something you will need to know how to apply. We're going to do lots of exercises as well next week. And then we're going to revisit maybe something you learned about invariance and variant. However, it's more in the slightly narrower context about loops, because loops are very important construct that's going to be included in your program, especially whenever you want to argue about correctness versus termination. You will need these two constructs, right? We'll talk about them most likely next Wednesday in the last class. Now, the correctness proof for the loops, I'll give you guys some exercises as well to try, okay, before the exam. All right, so what I need to talk about right now, I will switch to the iPad very soon. So I think this part about slide number 3 and also slide number 4 and 5, right? So these 3 slides are something I'm going to cover on the iPad in the next few minutes, maybe up to 10 minutes. Okay, that's something you can definitely read it by yourself. But I'm also going to cover that here. Okay, so we talk about assertions. The assert keyword in TLA plus. Okay, we'll talk about assertions. And the assertion is basically just Boolean condition. And you can use the assertion for either precondition, postcondition, or invariance. Precondition, or it can be used for postcondition, or it can be something that should be globally true, invariance. So these are the 3 main purposes for assertion. And let's now review some basics, because we're going to keep talking about weaker versus stronger, right? We talked about it already maybe once or twice, but I think it doesn't hurt to repeat again. Okay, let's do a simple example. One assertion could be, let's say, x larger than 3. Another one would be x larger than 4. Okay, so we deliberately choose 2 assertions that look very similar, also very close to each other, but they are not exactly the same. Okay, so to really define whether an assertion is weaker or stronger, you can think about in terms of the set comprehension, meaning that what would be the set of values of x that's going to satisfy this assertion versus this assertion. Whichever set that's going to be bigger is going to be the weaker one. Whichever set is going to be a smaller is going to be a stronger one. Okay, let's now do that quickly, right? So this concept here is very important. Okay, so let's say x larger than 3 is going to be all the x value such that x larger than 3, obviously. And let's now numerate them. The smallest value should be 4. Agree? 4, 5, 6, all the way to infinity, right? It's going to be 4, 5, 6, 7, all the way. All right, that's one set. Think about that'll be the set of satisfying value. Satisfying values of an assertion. Okay, let's do something very similar for the other one. That one there is going to be all such x where x is larger than 4. And as you can see, the smallest value in the set cannot include 4, right? It's going to be starting from 5, 6, 7, and etc., right? Obviously, this set over here in the pink is strictly smaller than this. So we will say that this predicate here is going to filter out more value in the satisfying set. So this one here is stronger, right? That's intuitively what it really means. Let's visualize that. Okay, so we got over here, let me just be consistent. So let's say this is the pink one. That one will be x larger than 4, including 5, 6, 7, etc. Okay, this is stronger one. And the weaker one is the green one here, conceptually. That one there is really the x larger than 3. And whenever you got this kind of construct over here, you want to know what is the member that is actually here but not here. Obviously, 4. Right? So you can think about this value over here, for example, 4, which is going to make x larger than 3 is going to be true. However, x larger than 4, the stronger one, is going to make it false. Okay? And let's now make a little bit more annotation here. And for this set over here, you got strictly fewer satisfying value. This will mean that assertion over here is said to be stronger. Stronger in terms of the filtering ability for the value to be included in the set. And symmetrically, you can think about this one here. You got more satisfying value. That means this predicate over here is weaker. You can allow more values to be included. Okay. Okay, weakest versus stronger. Okay, let me say one more thing. So in general, if you're able to show P1 implies P2, if you're able to show that this implication is the case, right? So we'll say that P1 is the stronger one. And also P2 is the weaker one. Right? So that's maybe something you want to remember more easily. Think about implication. And later on, when we actually do the weakest precondition calculation, we'll actually have to use this weaker versus stronger. So it'd be nice if you guys can review before next Monday. So when we dive into the detail, you wouldn't get so lost. Okay. And some quick check with you. Okay, since now we talk about stronger, we talk about weaker, right? And then let's talk stronger and weaker is more like a relative. Whenever you got P1 and P2, you could want to see which one's stronger, which one's weaker. But in general, it is also possible you cannot really check exactly like weaker and stronger. It may be that, right? So maybe you got P1 over here, and also you got P2 over here. You cannot simply get like a subset relation diagram drawn. You may have to use this more general diagram over here. If that's the case, there's simply no implication. You cannot really say stronger or weaker. You just cannot. Okay. Let's say, for example, let's say P1 over here could be, let's say 1 less than or equal to x less than or equal to 5. You know, some interval, right? And also P2 could be, let's say, have some overlap, but it's such a different interval, basically. In that way, you might say maybe minus 2 less than or equal to x less than or equal to 3. Right? If you think about these two intervals, you cannot really say one implies the other. You cannot say that. But they do have some overlap. Okay. So now in this case, cannot claim one assertion is stronger or weaker than the other. This is also a very important point. We cannot always take some arbitrary two predicate and say which one's stronger, which one's weaker. We can only say that if we can prove the implication relation between them. It's a very important point to note as well. All right, two more things. Given all these definitions, I want to ask you guys about two things. What would be the strongest predicates? What assertion? Strongest in the sense that because the stronger an assertion is, the fewer values it will allow to be included. Farris first.
False.
False. Nothing can satisfy false. So the corresponding satisfying value set will be just empty. Right? That one's obvious, right? Now you can see where these kind of all terminology come from. Adrian, I'm pretty sure you know. What about the weakest assertion?
True.
Absolutely, right? Because everything is satisfied true. So everything will be included in the corresponding satisfying value set. Okay, weakest assertion will just be true. Okay, like that. All right, any question? Good. Yeah, I think this will be good. I think let's just cover only this basic about stronger, weaker, and then on Monday, I'm going to adapt these two terms into the context of algorithm, and especially talk about what does it really mean. We have a stronger versus weaker precondition, and what does it really mean when we have a stronger versus weaker postcondition? And then we'll go from there into the whole triple. That's something we'll do. Okay. Okay, let me just make sure. So before I take your questions, let's now talk about some tips, right? So for your written test number 2, okay, of course, you want to be very clear about the definition, about the future, global, and also next operator. Okay, formulation, you got to be very clear, especially how do you prove versus disprove them. There will be no written question for tomorrow, like a typing, all multiple choice. Okay, if that helps you. All right?
We're not sure.
We're not too sure. Okay. At least no written part. How about that? Okay.
Multi-correct or single correct?
They will be, oh, yeah, that one I'm not going to lie. So there will be some question where you got a multiple correct. You do have some. Yeah. But guys, how about this? There will be some true-false question. Like a binary, right? For true or false. There will be some. Let me finish the tip first, and I'll take a question. How about that? Okay. Yeah. Okay, definitions, proof versus disprove. And also, the in-class exercises we have done, whenever you try to do maybe a path satisfaction versus model satisfaction, that's also important. Okay. Path versus model satisfaction. Okay, I forgot the exact number, but I think it's about 9 questions. Okay, so your best preparation for tomorrow, I would suggest review the path versus model satisfaction exercises we did in the class, review them. And since there'll be no written part, so I think maybe try to be more efficient in determining whether something should be satisfied or not satisfied. Justification will be left to the exam. Okay, I'm telling you. Okay, yes?
Sorry, the approximately 9 questions, is that just regarding math versus model satisfaction?
Just overall, you got 9, about, I forgot exact number, but I don't think it's more than 10, about 9. About 9. It's pretty much set, right? I'm not going to create any new questions, right? But I forgot exactly whether it says 9 or 10. Yeah.
Would it be like that we're given a path and then like a few of the properties that satisfies or dissatisfies the
Something like that. So I might say a path, or maybe I'll give you a diagram like the one on your slides, and then I'll say now consider the model satisfaction with respect to maybe S0 or S1, something like that. And the choice can be I give you the diagram, and then I give you maybe 5 formula, choose those that will satisfy, or choose that are not satisfied. Right? Only 2 tips, but I think that's pretty much enough. Okay. But guys, you can feel free to ask me a question, contents or maybe about the test itself. I'll try to see if I can answer. If I cannot, I will be honest. Anything? Yeah.
So Dr. you had a written question, it was exercise 2, and it was a multiple choice. I quite didn't get it. Can you explain that again?
You mean for written test number 1?
No, it was sort of the literary.
Which one? You gotta tell me which one.
Yeah.
All right, guys. Meanwhile, is there any other question you want to ask? Yeah, go ahead.
So like the complexity of like how the nesting of
Okay, for the nesting here, I would say, okay, I'll also be very honest with you. For this written test, I really want to check just about basic understanding. Understanding about GF, FG should be enough. Or GF implies FG, FG implies GF. You know, the ones we talk about in the class.
it would be like GXF.
Yeah, there wouldn't be any new nesting you haven't seen. How about that? I'll save that for the exam. All right, anything else? And my number 1 tip, I really think the written test is definitely more straightforward. Don't miss it. Grab your marks.
Okay.
Not exactly free, but should be much easier. How about that? All right, thank you so much. I'll see you tomorrow.